Testing, testing. Trying something a little different today. I'm gonna go ahead and start the stream before I let the students in because it has been taking us like 15 minutes. I should be able to see my desktop at this moment. So I am just trying to get my confirmation that the test is in here. Okay, I know the audio is working. A little different today. I'm gonna go ahead and start the stream before I let the students in because it has been taking us like 15 minutes. I should be able to see my desktop. And I think what's been happening is that maybe somehow the amount of students that I have on the Zoom call is affecting its ability to like live stream or something. I think that's what's been going on. So we're gonna see how this affects it. We need that. We also need, okay, I think we have something. Can we just work on the chapter 1 review somewhere? Another place that I could go. That's not what I want to do. Let's cancel. Let's see if I can pull those up. Okay, we're gonna go with this. All right, so welcome scholars. So let me see. So your exam 1 should be available as we speak. So what we're going to do for this week was try to devote today entirely to chapter 1, and then on Wednesday we'll devote to chapter 2. I did have a student email me like several questions throughout the night. So I'm going to pull those up and we're going to start with those. And I'll just get the second wave of students at the 15-minute mark, right? And if you have questions, the best practice is for right now for today, if it's like a homework, click on the Ask My Instructor, and what that'll do will send me a screenshot of your question, and I can pull it up now and we can talk about it. If you're working on a quiz or an exam, just screenshot it, email it to me, and then I can pull it up and we can talk about it, right? So let me start by 777s. Let me start by pulling up this question from the student. Okay. So find the derivative of this function, right? So this, okay, yeah, let me get a copy of this. All right, let's zoom in. Okay, this comes from section 2.6. Now I know we said, well, the goal is to devote today to chapter 1, but again, since the student requested this one, I'm going to go ahead and work on this one for right now, just because someone requested it. Let me copy and delete, and let me go ahead and kind of get some more students in here, because I kind of did it. I started right at 6, right? So if you're even late by a moment, then you're going to fall into that second wave, and I don't really want you guys to miss out. I don't want you to miss out, but I can't make you be here like early and on time. Let's see. Let me check on you guys again, but I also can't keep stopping to let students in, because that's very disruptive. 1, 2, 3. Okay, let them in. All right, so let's see if we can make our way through these questions that were asked by the student. I know my pen is low. Let me see. Let me charge this thing. Give me a moment. Here. This. I usually don't think about my pen until it's time for me to use it, and then by then it's usually too late. And so I was so focused on having a clean stream today, I didn't even bother trying to charge the pen. Okay, so we're just gonna kind of talk through this one for right now. Okay, so when I first got this pen, it said that 15-second charge should keep it charged for like 30 minutes, right? So I'm just stalling a little bit to give it like 15 seconds and see if that works for like the next 30 minutes or so. Find the derivative of the following function, right? So this derivative is going to be similar to the derivative of e to the x. Remember, the derivative of e to the x is itself, but the only augmentation here is we need to multiply by the natural log of a, right? So long story short, okay, when we go to find, we'll call it dA by dt, the 530 is just going to persist. An exponential derivative is itself to the power of t. Then we're going to say times the natural log of that base. So then 1.727, okay? So then I think from there, we would have to use the calculator, but I think we're positioned to answer the question. Let's see, let's go like this, type an exact result. Okay, well, let's see if we can get it exact. Okay, let's go this, turn this off. So then what we got was what, 530. Oh, you're doing this thing. Okay, so 530 times the exponential 1.727 to the power of t times the natural log. So I'm just going to put ln, okay, of the base, which is 1.727. Now, I don't know how to get more exact than that. We could crunch those numbers and get an approximation, but I'm going to go with this because it says an exact answer, okay? I'll check attendance again in just under 9 minutes. I hope everyone is doing well. You enjoyed your weekend, right? We are rapidly approaching spring break, right? So right now, again, our exam 1 is available. You can actually ask me questions from your exam right now. If you're working on it, you have questions from it. My recommendation, if you're working on your exam and you want to ask questions, screenshot it, email me, and stop me. Say, hey, Mr. Pfeiffer, I had a question for my exam. Can we talk about it? And we can talk about it right now. It's totally okay. Okay, so we got that one. So I'm going to piggyback on this live stream, and I just have to tell the students, hey, I answered those during their live stream. Let me go to the next one, which is this one. Okay, I'm just going to open it up. And so basically what it is the student used to ask my instructor. Now let's look at this one. This one comes from section 2.6, question 54. And I think the PS stands for like physical sciences. It says the intensity of sound is given by this, where L is the loudness of the sound is measured in decibels, and I sub 0 or I naught is the minimum intensity detectable by the human ear. Okay. Find I in terms of I naught. Okay. Okay. For the loudness of a small engine, which is 70 decibels. So then basically just plug in L equals 70, and then that's going to be your I in terms of the I naught, right? So it's going to be I naught times 10 to the power of, let me see, 7. A tenth of 70 is going to be 7, right? So it's going to be I naught times 10 to the power of 7. Exponential notation, right? Okay, I feel like this is okay. 10 to the power of 7. Okay. So then part B, again, these questions come from a student had these questions in the homework. Find I in terms of I naught for the loudness of a quiet sound, which is 10 decibels, right? So if we let L be 10, 0.1 times 10 is 1, so then that's just going to be a 10 here, right? 10 to the power of 1, which is just 10, okay? It says compare your answers part A and B. The intensity of a sound. So the small engine is as loud as the quiet. What? No, that doesn't even make any sense. The small engine is 10 to the power of 5 times louder than the quiet sound. Loudness of a small engine and a quiet sound. Let me see, the small engine. No. The small engine is 10 to the 6 times louder, right? Because if we multiply by 10 to the 6, then we add those exponents, we get 10 to the 7. Let's go with C. Okay. For part D, find the rate of change of I with respect to L. Okay. So basically they're asking us to take the derivative. Okay, that's fine. Okay, I think we can do it here, right? So that I naught is just, you treat it like a constant. I know it's no number given, but in this context, it's just a number, right? So however, if that were any number, you just treat it like it's a constant. We call it, it's treat it like it's a constant, right? So when we take the derivative of this guy with respect to L, we're taking the derivative of 10 to the 0.1 L, right? So that's taking the derivative of an exponential, which is going to be itself. So the first part is we're still going to have our 10 to the power of 0.1 L, okay? But then the added stipulation is we have to say times the natural log of the base. So we're going to leave that as the natural log of 10. Okay. I think another part is we need to say times the derivative of the power. The derivative of the power, in this case, is just going to be 0.1. All right, so I'm just going to say times 0.1. We could kind of move some stuff around, but I think that should get it. Okay. So there was an added component that we needed to do with the power. Interpret the meaning of the derivative of I with respect to L. So that's the rate of change of the intensity.
Professor?
Yes.
How'd you get D?
D, right? So we took the derivative. We treat I like a constant. So it's really just, that constant just kind of goes out in front. So that's why they already gave us the I sub 0, right? And then we're really just taking the derivative of that 10 to the power of 0.L, right? We're taking the derivative of 10 to the power of 0.L. So that's the derivative of exponential. The derivative of exponential is itself times the derivative of the power times the natural log of the base. And that's essentially what we did. You see itself times the derivative of the power, which is going to be 0.1, times the natural log of the base. Okay. And then for part E, it says interpret the meaning of the rate of change of I with respect to L. That's how the intensity changes as we increase by 1 decimal per change in decimal. Is the rate at which the sound travels? No. Is the loudness at which a human ear? No. Is the rate of change of the loudness based upon the frequency? Is the rate of change of the intensity based upon the loudness? Yes, let's go with D. That one sounds accurate. Okay. We got a couple more minutes before I do my second wave of attendance. Okay, so this was the second question that came from Mr. Lowe from the evening. Again, if anything isn't clear, just stop me. We can talk about it some more. And this is being live streamed. I did it a little bit different today, where I did notice, again, in the spirit of mathematics and pattern recognition, I did notice that it was taking us like 15 minutes to get this image pushed. And so what I think was really going on, the more students I have on Zoom, the less effective it is at pushing to YouTube. So I was like, okay, let me go ahead and start the live stream before I let the students in, and then let's see if it works. And sure enough, it worked like a charm. Okay, let's go on to the next one. So I think he sent like about, let me see, 2, 4, 6 questions in the night, like back to back. So we're just knocking them off one by one, right? So this next question, and if we just happen to talk about chapter 2 today, we'll go back to chapter 1 on Wednesday. So this comes from section 2.1, question 51. I don't know what the BE stands for, right? Business economics, maybe. I'm just guessing, but that doesn't matter. Okay, so let's look at it. In 2012, let me see the time. Okay. In 2012, 34.1% of all glass containers were recycled. A beverage company used 350,000 pounds of glass containers per year. After recycling, the amount of glass in pounds still in use after 2 years is given by this formula. Find N of 5, find N prime of 5, and explain its meaning. When will 5% of the original glass still be used? Okay. And we got some solutions here, but it's this journey, we're less concerned with the answers, and we're more concerned with how do we arrive to those conclusions, and what do these things mean, right? So N of 5. So with N of 5, they're just saying, hey, plug in when T is 5, and then it says that this formula, this is going to be amount of glass in pounds still in use after 5 years, right? So I think we see the result there. We can go ahead and confirm that number. Let's go ahead and break open our trusty, dusty, rusty calculator. Okay. I'll check attendance in just a moment. I see the time. We're pretty much at that time for the second wave. Okay, that looks good. So let's put this in our calculator, right? What I'm going to do is I'm going to go to my y equals and put in the original, the 350,000, okay, parentheses, 0.448 to the power, instead of T, I'm going to put X, right? So that's a copy of the original, okay? So then what I'm going to do, to the left of the clear button is a button that says VARS. I think it's short, it stands for variables. I'm going to click on that. I'm going to go to the right to go to Y variables. I'm going to click on number 1 for function, and I'm going to click on number 1 again to call in the function I just typed in. And so basically we're going to let T be 5 or let X be 5, and we should get that 6,316.23 pounds, and you see it there. Okay, so all we did for part A, we just typed in the original function, plugged in T is 5. That's what the calculator output. It says round to 2 decimal places, right? So you can see it there. Okay, so then for part B, it says find N prime of 5 and interpret this meaning, right? So they're asking us to take the derivative. So again, I think I could do it in my calculator, right? Now, you know what? I think this can calculate derivatives. dy by dx, right? Let's try number 6. Oh, no. That's not what I want. That's not what I want. Stop. Okay. Calculate. Okay. Let me check one other thing. Math. I think this can. Fmin in derivative. No, there is a way to do it, but I'm just gonna go with what we have. Okay. So if we were to calculate this derivative manually, again, that coefficient at 350,000 persists. So I'm just gonna go ahead and type 1, 2, 3, right? That persists. The derivative of an exponential is itself. So we're still gonna have this 0.448. In this case, our T is 5, okay? So we're still gonna have that guy, but then we need to say times the log of the base. So we're gonna say times the natural log, nope, that's not natural log, not second, just the natural log of 0.448, okay? Let's get that extra 4 in there, okay? So when we go to take the derivative, this is what we're gonna get. We should get After 5 years, the amount of glass still in use will be, okay, so we didn't, okay, so we need to calculate part B. All right, and so you see the second part of part A is there. Okay. So round to 2 decimal places. Let's see. The rate of change, right? So this is going to be the rate of change after 5 years. This is how much less glass is going to be in use after 5 years, right? It's the rate of change, right? Round to 2 decimal places. Let's try that negative and let's see if it works. We want that to be gone. Okay. All right. Let me just do this one and I'll check on these guys. Oh, come on. Turn it off. I don't know how to let that be the default setting. Okay, so we took the derivative and we plug in after 5 years. This. Okay. It says round to 2 decimal places. We're going to do negative. We got 5071.7. All right, because after the 9 is the 5. The 5 tells us to round up. So then the next one after 69 will be 70. Okay. Cross our fingers. All right. Okay. So this expression means that after 5 years, the amount of glass still in use is changing by n prime of 5 pounds per year, right? Every year. This is a rate of change. Okay. 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 I kind of let me see. When will 5% of the original amount of glass still be in use? Let me see. So we were solving for T. It seems like we let the original equal 5% and then solve for T. Okay. I think I'm going to just do this in the calculator, right? So instead of writing 5%, more than likely it should be 0.05. Usually we write that as a decimal. So then we would have 0.05 divided by that 350,000. Okay. Let me see if we divide, we would take the log of that, insert. I'm just trying to wrap it up so that I can check on my students. Log, okay. And we need to close off that log, okay. And then the final step is divide by, no, wait a minute. Yeah. Divide by the log of 0.448. I probably should write that out. Let me divide by the log of 0.448, okay? And then 5% of the glass will still be in use after 2 decimal places, so 63, almost 20 years. 19.63 years. That's a reasonable answer, 19.63 years. Let's see. Let me write it out. Let me see. Still being used. Unless it's not supposed to be 0.05. Let me check it one more time. So if you have 5% divided by 350, okay. We take the log on both sides, so it's going to be the log of whatever that is. Okay, close off the log. That looks good. Let me think. Then we divide by the log of 0.448. 20 years. Round to 2 decimal places is needed. 63. Let me see. Only other thing I could think is instead of 0.05, it might supposed to be 5. What I'm going to do is view an example, right? I'm trying to wrap this one up so I can get to the students. Let me kind of just jump to the end, and I want to compare to how they did their last one because I know we're close, and I think it's just something about. Let me see. Yeah, that's fine. The original. That's fine. 2.1. Okay, let's see. What are we doing wrong? 500, right? 5% of the original glass still be in use. Okay, wait a minute. I might need to write this one out. I might be moving a little too fast. If we look at theirs, there's the original, right? Now, where's the 25,000 coming from? Where is it? When will 5% of the original amount? Oh, okay. Okay. If we started with 500,000 and we finished with 5%, 5% of 500,000, I think is 25, right? So we need to incorporate that into our maneuver. I probably should write it out, but I think I'm still not going to. All right, I think I got it. I'm just gonna go ahead and do it because again, I'm trying to get to you guys. So if we start with 350,000, we're gonna finish with 5% of that, right? So when we say that final amount divided by the 350, we should have 0.05, right? Okay, we've divided by the 350. So then we would take the log on both sides. So then that would give us the natural log of this guy, okay? And then we're gonna say divided by the natural log of 0.448, right? I should have written it out, but you know, it's okay. And then that should give us T, 3 years, okay? 3.73, let's try 3.73. 3.73, okay? All right. Okay, so I was rushing a little bit. If I need to go back and write something out or go over something again, we can talk about it. Let me take a moment to get the second wave of students. Let's see. I don't like to stop my stream because this image is delicate. So we're just gonna have to kind of go with it. Let me see. So this one. This one. This one. This one. Okay. Okay. It's everybody, right? I think I got them all. Let me check him. I think we're good. All right. All right, gentlemen. If you're just joining us, welcome. What we're doing, the original goal is to so you know, your exam one is available right now. We just kind of been going through some examples. I got caught up on this one on the last part of this question. So the goal originally is to devote today to just focusing on chapter 1 and then Wednesday to chapter 2. But we started with going through questions requested by a student, and they all just happened to be coming from chapter 2. So it's looking like more than likely we're just going to focus on today and devote it to be towards chapter 2, and then we'll devote Wednesday to chapter 1. Also, if you're working on your exam right now, you're more than welcome to you could screenshot your question, email it to me, and then unmute yourself and say, "Hey, Mr. Pfeiffer, can we talk about this question? I just emailed it to you." If you're working through the homework, I would encourage you to use the Ask My Instructor. It'll send me a screenshot of your question. That's how I'm pulling up these questions that we're working on now, right? So let me go to the next one. We still got 3 more. So let's keep going, okay? So we're just pulling up the next question that was requested, and this comes from, drum roll please. This comes from section 2.6, question 39, and we're asked to differentiate, okay? I think I'm gonna do this one here on Pearson because maybe not. It's looking a little bit involved. I think I can do it. I think I'm gonna just go with it. If I need to write it out, I will, but I think I can do it here. So the main operation looks like it's division. So we're gonna do the quotient rule first, which is low D high minus high D low over low low, right? Again, the quotient rule, low D high minus high D low over low low. So the low, let me do my fraction. The bottom, which is this, 5x plus 7, times the derivative of the top. The derivative of the top is going to be itself, 2 to the power of x. Nope, that's not a 2. 2 to the power of x times what? The natural log of 2. When it's a base other than e, you have to say times log of 2. So that's the bottom times the derivative of the top minus the top, which is this, times the derivative of the bottom. The derivative of the bottom is just 5. So that's low d high minus high d low over low low. Low low is going to be, I'm sorry, it just sounds funny to me, but that's what helps me to remember it, right? Because it's kind of zany. That thing, come on, I need that to go away. Thank you. Okay. Let's see, can we simplify? We can factor out a 2 to the x, but it doesn't look like we can get anything to cancel. Okay, I think I'm gonna go with it. I'm gonna just submit that. Okay. So hopefully that was okay. Okay, let's see what else we got. So again, these are just questions. We got 2 more questions from a student. Okay. And again, all he did was use the ask my instructor. A lot of times when you guys leave at the end of class, we go back and forth for like another hour. You know, he's like, can we go through these questions? I'm like, yeah, sure. And, you know, I'll be like giving them all, and I'm like ready to black out, and I pass out, but it's all good. I'd rather it be like that, you guys asking questions, you know, things of that nature, than staying mute, right? I want you need to be asking questions. And if you're not going to ask me, hopefully, you know, you have somebody that gets it. If it's not a classmate or a tutor, you have somebody that you feel comfortable like talking about this stuff with. You know, I'm not for everybody, right? You know, I do the best I can to try to, you know, encourage you guys, but I do acknowledge that, you know, I'm not for everybody. You know, anyway. Okay. So here we're taking the derivative. Again, this just happens to come from chapter 2, section 2.6, question 35. I guess we need to just devote today to chapter 2 since we're doing all these chapter 2s. We'll finish these and then we'll kind of jump around chapter 2. So it looks like we have to do the product rule in conjunction with a few other rules. The product rule is what? First times the derivative of the second plus the second times the derivative of the first. All right. Okay. So the first, which is this guy, times the derivative of the second. An exponential is its own derivative. And then we have to say times the natural log of the base, which is 1.1. So that's the first times the derivative of the second. Now we're going to say plus the second times the derivative of the first is going to be 3x squared. All right, that's it. All right. We could factor out that 1.1x and the squared, but I'm inclined to just submit this. Let's go with this. Okay, let's see what else. I think we got one more, and then we'll probably just go ahead and stay in chapter 2. Come on. And this comes from 2.6, question 23. Find the derivative of this function. Right, I think we did one like this, but let's just knock it out real quick. So the derivative of an exponential is itself. The 530 just persists. Let's click here. So the 530 persists. The derivative of the exponential 7 to 7 to the, let's do it like this, to the power of t. But then we also have to say times the natural log of the base, 1.727. Okay, that's it. I'm gonna go with that. Okay, I think that was it for those. So let's see. And again, if you guys, is this, so again, I'm just going to kind of jump around chapter 2. We just did several from 2.6. How much time? We're about, I think we're about halfway, maybe a little bit more, a little shy of halfway. I guess let me just start from the beginning, and I'll just spend like a few minutes, like maybe 10 minutes or so on this one. And you know, again, just if you want to jump around, if you want me to do something else, just request it and we can talk about it. Okay, I'm going to skip this one because that's not chapter 2. I'm going to go until I get to a question from chapter 2. That's chapter 1. We want to talk about chapter 2. Okay, let's look at this one. Graph the function and identify the domain, range, y-intercept, and state whether the function. Let me kind of zoom out some. Okay. So if we use transformations, right? E to the x, exponential is similar to d. But now when we start to account for those manipulations, like if we use the transformations from college algebra, working our way from the inside to the out, the innermost transformation, we can say we multiply the inside by that 1/2. So multiplying the inside by a number between 0 and 1 causes a horizontal stretch. Then multiplying the inside by a negative flips it horizontally. Okay. So instead of exponential growth, it should be exponential decay. But then we multiply the outside by a negative. So that's like the y values go from positive to negative. So then I think the only one that captures those transformations is going to be A. All right, let me go with that one. Okay. So I used the transformations from college algebra. Also, you could have like chose several values of x and found the corresponding y and plot the points. All right, you can do that. That's okay. The domain. So if the graph is A, then the domain, based on that image, the domain of exponential is all reals. So this domain is going to be all reals. Negative infinity to infinity. Okay. The range, right? Now, generally, an exponential with no manipulations, the range is 0, the open interval 0 to infinity. But based on these manipulations, the very bottom is going to be negative infinity and the very top is going to be 0 with the parentheses. So we're going from negative infinity to 0. And again, 0 gets a parentheses means we get really, really close to 0, but we do not include 0. All right, so we're going to go with that. Okay. The y-intercept. So the y-intercept is where what? X is 0. It's looking like that's going to be -1, right? If you let x be 0, it looks like we get -1. Let's try it again. 0, e to the 0 is a 1. Oh, ordered pair. Okay, okay. So then 0, 0, -1. 0, okay, that's fine. So as we trace it left to right, it's steadily increasing. So we're just going to say it's increasing. Okay, that wasn't too terribly bad. Let me check on you guys in Zoom for a moment. Oh. Just a moment. This one. Okay. All right, let's keep going. I'll do a couple of more here. It says an initial, let's zoom in some. An initial investment amount P, an annual interest rate R, and a time tier given. Find the future value of the investment when the interest is compounded annually. This is 2. I'm going to skip this. This is like college algebra. I'm just going to skip this one. Use the calculator to find the natural. Now, if anybody needs me to go back and do that one, I will. Just say, hey, can we go back to that one? And then we can go back. Use the calculator to find the natural log, base E, right? So calculator, trusty, dusty, rusty. We're just going to say natural log of 45 and see what happens. Around the 4 decimal places, 8067. 8067. Let's see what's next. Let's see. I'm going to skip that one. Given that the natural log of 7 is this, so then it should just be that, right? Because, okay, let me see. this is going to be the product rule, right? Where for logs, so this is going to be the same. Thank you. Stop. This is going to be the same as the log of 7 plus the log of e. The log of 7, you see it there. The log of e is going to be 1. So you say 1 plus that result. So then it's going to be 2.9459. Okay. So again, the rules for the product rule for logs, the log of a product is the same as the sum of the logs. So then that product can break apart into the log of 7 plus the log of e. Log of 7 is given. Log of e is 1. 1 plus what's given is the result that we got. Okay. Solve this equation. Okay, that's fine. So I'll take some notes here in this space, in this window. If we're going to solve for t, we want to get that out of the exponent. So first thing we want to do is take the log of both sides, right? If we take the log of both sides, on the right-hand side, we're going to have the log of 7. So I'm going to just put it like this for now, okay? On the left, we're going to have this negative 0.515t. So then ultimately, t is going to be the log of 7 divided by that negative 0.515, okay? Simplify your answer, type an answer in the integer or decimal round to the nearest thousands, okay? So then this is going to be approximately, so we're going to use our trusty dusty rusty. We're going to say, we can do the log of 7 divided by, the bottom is a negative 0.515, okay? That's decent. Nearest thousandths, so 3 decimal places, 778. 778. Here it is. This guy. So then we get a negative 3.778. Okay, let's get rid of all this other stuff. Okay. Let's go on to the next one. Find the domain, okay, and then graph the function. So in general, for a log function, the domain of a log is the non-negative real numbers, right? It has to be strictly larger than 0. So long story short, that 5 minus 3x has to be strictly larger than 0. All right, again, that 5 minus 3x, I'll kind of take some notes here. 5 minus 3x has to be strictly larger than 0. So if we solve that inequality, you can add the 3x to both sides, divide by 3. So then you're going to get, basically you're going to get 5 over 3 is strictly larger than x. You're going to get something like this. Okay. So then if 5/3 is bigger than x, that means that x is strictly less than 5/3. So we need to write that in interval notation. Okay. So let's do that here if we can get this to behave. So this in interval notation, if x is smaller than 5/3, it means we're talking about all the numbers to the left of 5/3. So the far left is going to be negative infinity up to 5/3. Because we cannot be equal to 5/3, it gets a parentheses. Okay, let me zoom out some. And let's get rid of all these notes that we don't need right now. Okay. And again, you have to stop me if anything is not clear or if you want to talk about something else. Okay. Or if you have questions, or if I just need to kind of like slow down, because I know I'm kind of like just breezing a little bit. Okay. Let's see, can we get this to display a little bit better? And then graph, let's see. Okay, so natural log, if we consider in terms of transformations, first we multiply by 3 on the inside. That's going to cause a horizontal shrink. It's going to smush it horizontally. Then we multiply the inside by a negative. So that's going to flip it horizontally. Okay. So it shouldn't be A or B. It should be either C or D. And then we added 5 on the inside. That's going to cause it to move to the left by 5, right? Okay, so it should be either C or D. The only thing is, I might need to rewrite this, but I'm going to go with the narrative that I just described. So I'm going to go with D. If it's C, then I can give an explanation how it could be done too. Okay, so I should have gone with my intuition, right? So in the way that it's written, we actually need to rewrite this guy. Let me think. What you have to do is like, you got to like factor out. You got to factor out that negative. That's what's throwing things off. So when you factor out the negative, you're going to have a negative times 3x minus 5. Once you put it in the proper form, which we didn't do, which again, it should have moved it to the right by 5, right? So it's just the order that's kind of got a little thrown off there, but we're going to go with this. All right. Okay, anyway, so okay, let's get out of this section. Let me see if that's 2.1. Let's look at 2.2. Let's spend some time there. It's here. I don't want to. Where is it? Here. Okay. Let's go here. Let's go to view. Allow. All right, so that was 2.1. Let's spend some time on 2.2, maybe like 10 minutes. Hey Siri, set a timer for 10 minutes.
10 minutes, starting now.
Okay, so let's work on 2.2. It's only 8 questions. Let's see what we can do. Okay. All right, so use the graph of E and transformations to sketch the graph of the exponential, determine the domain and range. Okay. Okay, so I'm going to click to enlarge. We're working with the exponential graph. So that's going to be the upper right. So I'm going to click on that one. And I'm just going to click on the origin. I'm just clicking anywhere. So now they're asking us to basically use transformations to graph this. Notice that we added a 2 outside of our base function, right? So that 2 is on the outside. So that's going to cause a vertical change. It should move it up by 2. Right there. No, not vertical stretch. Sorry. We want to go up by 2. There it is. Okay. So that's the only manipulation. I'm going to hit save. And I'm going to check. Okay. What's the domain? So in general, the domain of an exponential is all reals. The manipulation we didn't affect the domain at all. So this domain is going to be all reals. Every x is accounted for. For every x, you can find a corresponding y. So this domain is going to be negative infinity to infinity. Okay. So in general, the range of an exponential goes from 0 to infinity, the open interval. But because we moved it up by 2, instead of it starting at 0, it's going to go from 2 to the open interval from 2 to infinity. So we're going to say parentheses 2 to infinity. Okay. Again, if anything is not clear, you have to stop me. What's the y-intercept? Where does it cross the y-axis? So that's going to be, if you let x be 0, you'll quickly see that it says type an integer or simplified fraction. When x is 0, the corresponding y is 3. Okay. The horizontal asymptote. Generally speaking, for an exponential, the horizontal asymptote is going to be the x-axis, y equals 0. But because we moved it up by 2, now the horizontal asymptote is going to be y equals 2. And the only reason I'm able to like say this stuff like this is because a lot of this is coming from college algebra. And I mean, I do that like every day for the past decade. Well, nearly every day. Obviously in the holidays, but yeah, college algebra, that's where a lot of this is coming from. Take the derivative, right? Type in exact answer using radicals as needed. They asking us to take the derivative. Okay. So I'm going to take my notes here. Again, this is the quotient rule. Quotient rule is low D high minus high D low over low low. Okay, this isn't really chapter 2. I'm going to let this be for now. I want to jump to something that's from chapter 2 because our goal was to let today be chapter 2. We'll do this. Okay, differentiate. We can still do the quotient rule. Matter of fact, let me go back to the previous one because that one was interesting as well. differentiate, right? So this is just the derivative of e to the x, all right? So the 5 persists. E is its own derivative. So e to the power of 2x, you just repeat it. And then we have to say times the derivative of the power. So it's going to be times 2, which is going to make this guy a 10. It's going to make this a 10. Okay. Okay, let's go to the next one. So here, the quotient rule. Quotient rule is low D high minus high D low over low low. I can't say it with a straight face because it just sounds so silly. But it just brings some energy to it, right? Okay, let's give it a go. So low, the bottom is just this guy. We got this x to the power of 8. Okay. Let's fix that. Nope, that's not. There we go. So the bottom, low D high, so that's the derivative of the top. The derivative of the top is going to be itself, e to the power of 2x. Okay, this right here, okay, times the derivative of the power, which is just going to be a 2, okay? That's the bottom times the derivative of the top minus the top, which is this guy, this e to the power of 2x. Nope, fix that right here, okay? Low D high minus high D low, the derivative of the bottom is going to be 8x to the power of 7, okay? All over the bottom squared, a power to another power we multiply, so 8 times 2 is 16. Now wait, let's do this. We're going to say to the power of 8, and we're going to do this like this. We're going to say squared, right? Can I get rid of that? Thank you. So before we submit this, notice that, let me see, both terms have that e to the 2x. They both have the 2, and they both have 7 x's, right? So we're gonna simplify this down some. Okay, so this isn't the fully simplified form. There are things that we can factor and cancel. So both terms on top, they both have a 2. Okay, let me do my fraction. So they both have a 2. They both have the, let me see, x to the power of 7. All right, they both have x to the power of 7. And they both have e to the power of 2x. E to the power of 2x. Okay, we can factor that out of both expressions, right? So now from that first expression, if we remove the 2, the e to the 2x, and 7 of those x's, all that's left is a single x. Okay, so from that second term, if we remove a 2, then we have a 4 left over. Remove 7 x's, so that's gone, and remove the e to the 2x, that's gone as well. So only thing that's left is the 4. On bottom, now if that's a 16, right? We have 8 to the power, we have x to the power of 8 squared, so that's x to the 16. We want that x to the 7, right? So we're going to have, this is going to be, x to the 16 is the same as x to the 7 times, what is it, x to the 9, right? Because when we multiply powers of the same base, we add the exponents. So then 7 plus 9 gives us our 16. We want that 7 so that we can cancel them, right? And let's write the simplified form. We're going to do a fraction. This should be the final part. So those x to the 7s are gone, and all that's left, we have this 2, this e to the power of 2x, okay? We still have this x minus 4. Now on bottom, all we have is this x to the power of 9, and I think that's about the best that we can do. Okay, I just want to get rid of all of this. Okay. Okay, we're gonna cross our fingers. God is good, right? Oh, is my image frozen? Oh no. No, maybe not. Maybe somehow my thing, I think when my alarm went off, froze my thing, but we're good. Okay. All right. Let's see. Let's do another one. I mean, we could do it. Okay. So the derivative of e is itself, right? So we're going to have e to the power of x squared plus 5x, okay? But then we have to say times the derivative of the power. So the derivative of the power in this case is going to be what? 2x plus 5. Okay. Now, I'd like you guys to pause for just a moment, right? I just want you to think about this. You see how we're calculating these derivatives? Like we can look at it and we know the derivative. Remember when we first introduced the concept of derivative and we introduced it with that limit definition of the difference quotient, or that limit of the difference quotient definition? Remember how it took up like the whole page to do a derivative? And I was like, hey guys, you know, you can actually look at these and get the answers once we start going through some of these rules and theorems or whatever. Imagine trying to do this, something like this, with that limit definition of the difference quotient. Imagine that, right? There would be so many calculations all over the place, right? So, you know, math is all about simplification, right? The goal is to try to simplify some of these concepts as much as possible. It's not to be, sometimes it's unavoidable, but whenever possible. We're kind of running short on time. What is this? So I'm going to go ahead and go to the next section. Let's see. Where is it? Not that one, not that. I kind of want to close all these tabs. Let me kind of start over because these tabs are driving me nuts. Close out 12. Let's go here. Allow. Come on. You know I was signed in. Hey Siri. Okay. Is that what's causing it? Anywho, calculus. Okay, so we got about 15 minutes. Allow. Okay, so we're still working in chapter 2. So it just happened to be that we devoted today to chapter 2. Let's work on 2.3. Right, I know we were doing 2.6 earlier. Okay, let's do something from 2.3. Okay. And we want to go straight to questions from chapter 2. So I know it likes to kind of do some augmented review initially. That's chapter 1. Okay. This one comes from section 2.2, question 5. We're asked to take the derivative. So that first term, its derivative is what? 5x to the 4, 5x to the power of 4. The derivative of an exponential is itself, so we're still going to have negative 9e to the power of 3x. But then we need to say times the derivative of the power, so there's going to be times 3, which makes this a 27. Okay, I'm going to go with this. Okay. All right, so here, if we want to take the derivative, first thing is, we need to rewrite the square root as a power, as a rational power. All right, so that's the same as to the power of 1/2. So then we apply the chain rule, right? So the derivative of the outside function, that 1/2 comes down. Okay, 1/2 comes down. This e to the power of x plus 19 persists. We got to subtract 1 from the exponent, so that's going to become a negative 1/2. That's fine. And then we need to say times the derivative of the inside function. The derivative of the inside function is just e to the x. And then if we kind of like rearrange this stuff, it looks like on top, we're just going to have e to the x. Okay. On bottom, we're going to have 2 times the square root. Okay. E to the x plus 19. Are there any questions with this? You guys are quiet. I don't know. That usually silence means one of two things. Either you're getting it or, you know, for whatever reason, you're not asking questions, right? Let's go with this. I'm gonna submit this result. Okay. All right, let's go on to the next one. Okay, so with this, if we use the quotient rule, low D high minus high D low over low low, the bottom, okay, let's do our fraction. the bottom, which is this guy, x to the power of 9. Nope, like this. Low D high, the derivative of natural log is dx by x. So in this case, it's just going to be 1 over x. If that's 1 over x, this is going to turn into x to the power of 8, right? If we divide by x. So the bottom times the derivative of the top minus the top times the derivative of the bottom. Let's use our parentheses. And actually, let's put the derivative of the bottom in this case is going to be 9x to the power of 8, 9x to the power of 8. I just put it in front of the log. All over the bottom squared is 18, x to the power of 18, right? But notice that on top, we can factor out that x to the 8. Okay, we're going to have x to the power of 8. Now, what's going to be left over if we factor out x to the 8? That first term is going to become 1, very Zen-like. That second term is going to be what? 9 log x, okay? On bottom, if we factor out an x to the power of 8, the second term should be x to the power of 10. Now those 8s cancel. So this guy is canceled by this guy. And I think that's our result there. Let me just get rid of all this other stuff. Okay. Let's go with it. Okay. Let me check on you guys' Zoom. I know it's a little intense. We only got 10 minutes, right? So get this student. Yeah. Yeah, I got it here actually. I started to try to stream do a different setup, but I think I need a more powerful device. I was going to use like OBS and use my computer, but my experience in the past was that it just lagged and it had too many processes running and it just was not working. So I think I need to get a device specifically designed for like streaming, something that's more powerful. And I think that would help my streams, because I know sometimes, and you know, I kind of talked about what I did different today to kind of get it going, and it seems like it's working, the change that I've made. Okay, so the derivative of log is du by u. That's how I remember log, du by u. So when we're going to take this derivative, let's get rid of this, try it again. Come on. All right, when we go to take this derivative, du, oh, Jesus. So we need to do low D high, right? I'm tempted to rewrite this as x squared minus 4x to the negative 1. Okay. If what's given, the inside part, that's the same as x squared minus 4x to the negative 1. So then when we go to take the derivative, sometimes it's a little bit easier, right? If it's x squared, now the derivative is going to become just 2x minus, let's see, if it's minus 4x to the negative 1, the negative is going to come down. It's going to become positive. It's going to be 4 times x to the power of negative 2. Okay. So that's the derivative. That's my du, and then my u is the original, right? If I flip and multiply, x to the power of 3 minus 4, and we can distribute an x up here. So this is going to become x squared. This is going to become x to the minus 1. Now, I don't think we can submit it like this. To clear out the fractions, that 4 times x to the minus 1, that's the same as 4 over x. So if we multiply the top and the bottom by the LCD of the fractions, so let me rewrite this. So that's 4 over x, right? So to clear out that fraction, that's a complex fraction is basically where you have a fraction within a fraction. To get rid of those interior fractions, you multiply by 1 in the form of the LCD of your fractions on top and on bottom, right? In this case, multiply the top and the bottom by x. If we multiply the top and the bottom by x, then what happens is this becomes cubed. This denominator is gone, so that's just a 4. On bottom, this becomes to the power of 4. And this becomes 4x, okay? We could factor out a 2. I don't think we can get anything to cancel. So I'm going to go with this result. Okay, that was an adventure, right? This is being live streamed. You are welcome to go back. I need to go and update my videos. You know, I just have the raw videos on there, but make it so that you guys can find them. But, you know, you can always go back and watch this again, watch it with somebody else, watch it with a tutor or whoever you're working with, and break this stuff down. You have to slow down and you have to take your time. You know, with these interactions during class, you know, just absorb, just kind of listen and watch, and just try to absorb whatever you can. But you really don't get it until you're able to do it yourself, until you like just do it, right? You're not gonna be able to follow all of my stuff, and you won't see it until you do it yourself. If you're trying to follow like line by line of what I'm doing, it bores a hole in your head. It will drive you insane, right? It's even the same for me. Like I've never been able. I'm basically saying this from my experience. I've generally, whenever I try to follow either the professor or anybody else's work, I can't keep up, right? Because they say some things, they don't say some things. I know I don't see it until I do it myself. You know, I know you feel like you can't do it, but if you just try, sit down with somebody and just try, you get stuck. Then they get you past that part where you're stuck. Then you just try again. If you keep trying, you will get it. You will get it. But for these interactions, my recommendation is just to try to absorb whatever you can. Don't try to, you know, be too meticulous. Don't try to follow every little thing that I'm doing. Just kind of listen and get the gist of it and then try it yourself. Okay. Okay. Hopefully, you know, somebody heard that and it can help somebody to encourage them to keep going. Let's look at this. Let's zoom in a little bit. We got a little under 10 minutes. Okay. And again, I feel like that a lot of the intimidation comes because you're trying to follow my work. Like, just get the gist of it and then try it yourself. Okay. So it says the demand for a new computer game can be modeled by this guy, right? Where X is between 0 to 800, where P of X is the price consumers will pay in dollars and X is the number of games sold in thousands. Recall that total revenue is, what is that? Price times the number of units produced and sold. Okay, so find the revenue function. So basically take the function that's given, multiply it by X, and that's it. All right. So we're gonna say, if we distribute an X, we're gonna get 44X minus 5X times the natural log of X, okay? All I did was multiply that by X. Okay, let's keep going. Find the marginal revenue. Marginal revenue, it says R prime. Okay, so let's take the derivative, right? So if we just take the derivative of that result, the first term is just 44, okay? Now there we got to use the product rule. Let me zoom out one more time. My device is a little bit temperamental. Okay. So if we take the derivative of that result, the first term is just 44. Now we're still going to have this minus 5, but for that second part, we need to do product rule, right? So I'm going to do like this. I'm just going to focus on the X log of X. So the first is going to be X times the derivative of the second is 1 over X. So those together are going to become 1. Plus, let me see, the first times the derivative of the second plus the second, which is this, times the derivative of the first, which is this, all right? I feel like this is okay. Let me see, first times the derivative of the second plus the second times the derivative of the first. Okay, this looks good. Okay. Let's simplify and combine like terms, distribute all that jazz. So then we get 44 minus 5 minus 5 log X, okay? So then 39 minus 5 log X, okay? And we're gonna go with that. Right, hopefully we were able to keep track of everything. Marginal revenue, R prime of X. Okay, we're gonna go with this for now. Okay. How many units will be sold if the price that the consumers are willing to pay is 500? It was 50. So they want us to solve for x, the price, right? So we're going to let p of x be 50 and then solve for x. So if we solve for x by letting p of x be 50, first we're going to subtract 44. I'm going to put the exact thing here. So we're going to start with the 50, subtract the 44. Then we would say that answer divided by, so 50 minus 44, let's do like this. 50 minus 44. We're going to divide by -5. So divided by -5. And then all that's going to be left on the right-hand side, we're going to have the log of x. So to get rid of that, we have to say both sides. We have to say e to the power of both sides. Basically do the inverse of log, which is e. So over here, what we're going to have, if I can capture it, is e to the power of all of that stuff. All right, the 50 minus 44 over this -5. And that's the exact result. Let me get rid of this. This is kind of redundant, right? That's the exact result for the number of units produced, and then we just need to use our calculator. Round to the nearest whole number. So we're going to say e to the power of, now the numerator, we're going to say 50 minus 44 divided by -5, okay? Nearest whole number, let's see, what are we missing? How many units will be sold? Oh, practically 0. I guess people are not willing to pay that much. We're going to go with 0. Because basically what they're saying is that people are not willing to pay that much for this computer game, right? So let's put 0 here and see what happens. If it doesn't work, we'll take some time and try to get to the bottom of it. If we can get this to behave. I think I'm gonna go ahead. I'm gonna try to wrap up this question and we'll let that be it. So we're gonna put 0. Set p of x equal to the given price and then solve for x. Yeah, that's what we did. I probably should write it out. 50, right? 50 minus 44 divided by -5, e to that power. Did we put in the calculator right? E to the power of, oh. Wait a minute. Let's see. Get rid of this. I guess that'll be fine there for now. $10, yeah. $50. E to the power of 50 minus 44 divided by -5. Let's stop. Thank you. -5 e to the power of all of that. Okay. Only other thing I could think to do, let's do second enter. I'm going to put that -5 in parentheses. Maybe that's throwing it off. Because you want that minus that divided by -5 and then e to that power. What am I missing? How many is this? If consumers are willing to pay $50, whole number. 1? Is it 1? Oh, we got the same thing. Okay, let me see. I'm going to click on the view an example. And we're at part C. Let's just jump there. I'm trying to figure out. Maybe it's 1. We got that. Solve for X. 45, right? Multiply X, okay. So round to the nearest whole number. Oh, where's that 1,000 coming from? X is the number of games sold in thousands, right? So we need to basically say this answer times 1,000. Okay. So then 301. Okay. I knew there was 1,000 in there somewhere. I thought it was somewhere else, but that's fine. So 301 units. Yeah. So we're missing 1,000. Okay. Because of that experience, that's why I use like Pearson, right? I knew we were missing something. I couldn't figure out what it was. So notice when I couldn't figure out what I was missing, I just clicked on the view an example, right? And then I kind of compared it to what I did. I found what was different. And I was like, oh, duh. This is in terms of thousands of units, right? And we were doing it as individual units. Okay. I am kind of tired, and that's the last one of that section. Okay, so we're gonna go ahead and take that as, we're gonna stop there. Would you guys like to ask any questions before we go our separate ways? All right. So what we did today, I think I'm just gonna not submit this. We focused on chapter 2. Originally, we wanted to focus on chapter 1, but in the spirit of answering questions asked by students, answering homework questions, we did those first. All right. So if you want to see us go through those, just kind of go back to this video and go back to the beginning. And like the first 6 examples we did were whatever the student requested. And so because those came from chapter 2, we stayed in chapter 2. So then what that means is that on Wednesday, if there aren't questions, then I'll try to focus on chapter 1. And if you guys have questions, we could talk about those, okay? So before we go our separate ways, would anybody else like to ask any other questions, going once or going twice?
Professor, I still have some homework questions from section 2.5.
Okay, we can talk about it. Are there any other questions? Other questions, okay. So aside from these homework questions, if there aren't any burning questions, we're gonna go ahead and end the session here, and from one beautiful mind to another, enjoy the rest of your day. We're gonna go ahead and continue streaming, so if anybody wants to stay, you're welcome to stay and listen, but we're just gonna go ahead and kind of power through and work on some more questions. Go ahead. Did you do the Ask My Instructor bit?
Yeah, I think I did. Like I think yesterday.
So those are the questions that I did at the start of class.
Oh, okay.
Yeah, it was like 6 questions. So, I would encourage you. I mean, I guess we can do them now together, but I did it at the start of class, so you can always get the video, go back, and just look. I walked through each one of those. I think one of them I did even twice. All right.
All right.
But yeah, that's what we started. That's what we started the lecture with. All those that you sent, we just did it at the beginning of class.
Okay.
I would say just watch the video. If you still have further questions, just email me, or you know how to reach me. Email me, and then you can even get it. You could get on my Zoom, and if I get that notification, just wait like maybe 5 or 10 minutes, and I might get on. If I see it and I'm up, then I'll get on the Zoom like, hey, because like obviously I don't have a phone that you can call, but if you get on the Zoom and I see the notification, we can just do an impromptu session like that as well.
Okay.
Otherwise, we'll just you know how to kind of go back and forth with me.
Yeah. I'm about to go to the Ask My Instructor tab real quick.
You have other ones?
Yeah. These are from section 2.5.
Okay. Good chaka. I totally want to talk about this is just a brain. I'm just feeling the air until we get those questions submitted. I totally want to talk about like Quantumanium with the Ant-Man and the Wasp. I don't know. It seemed like it got bad reviews, but I'm like, I don't know. I enjoyed it. It was entertaining, but I did struggle seeing like the negative Black images. I struggle with I don't like seeing the negative Black images. I feel like, we get such a bad rap as is already, but you can't win everything. You know what I mean? But yeah, aside from that, I enjoyed it. I thought it was interesting. Yeah. Woo-hoo-hoo. Okay, I'm gonna go ahead and pull that one up. Morehouse. Start here. This comes from 2.5.
Yeah, I just sent them.
Okay. So this one comes from section 2.5, question 49. Morehouse. Okay. It says the concentration of a drug in the body decreases exponentially after a dosage is given. In one clinical study, adult subjects averaged 13 micrograms per milliliter of their drug in the blood plasma 1 hour after 1,000 milligrams of dosage. Find the value K and write an equation for an exponential function that we can use to predict the concentration of drug in micrograms per milliliters T hours after 1,000 milligram dosage. Okay, so we know we're working with an exponential function. Let's see. Concentration of drug decreases exponential. So we have exponential decay. All right. Okay. So let's take some notes here. Let's take some notes. I got plenty of time to charge. It should be fully charged at this point. Let's see. Let me start by getting a copy of the original. That looks good. Copy and delete. And let's just go ahead and paste. Let me see. Yeah, let's just paste. Okay. So this is a copy of the original. Okay. So we know we're working with an exponential function. So the general form, let's start with an exponential model. C of t. So we're going to say the concentration based on time is going to be C naught e to the negative kt. We did negative because it's exponential decay. Okay. Now let's see what components we have. What can we plug in? All that kind of jazz. We're asked to find K. So we know we're trying to solve for K. So I'm going to put a question mark for that. Concentration in drug, T hours after 1,000 milligram dosage. Let's see. The concentration of a drug in the body decreases exponentially after the dosage is given. In one clinical study, adult subjects averaged 13 micrograms of the drug in their blood plasma. So that's the concentration. 1 hour. Okay, so it looks like they gave us one ordered pair, right? They're telling us, let me see. I guess this is in hours, so we're going to say in hours. So after 1 hour, the concentration is 13 micrograms per milliliter. So that's one ordered pair. Micrograms per milliliter, okay. And the units for this is like 1 hour. I'm just putting the units for context, all right, 1 hour. And then it also says 4 micrograms per milliliter after 7 hours after a dosage, right? So after 7 hours, we have 4 micrograms per milliliter, okay? So we have these two pieces of data and we want to model it to the exponential function, right? So we're just going to plug these in, okay? Let me see. 1,000 milligram. So it sounds like what's the concentration at start? Should we put 0? No, that doesn't make sense. Let's just plug this in. We can calculate the initial concentration, right? So, because I'm not sure about that 1,000 just yet, we're gonna let that be for now. But let's plug in what we have, right? So the initial concentration, we're gonna let that be. We're gonna say e to the power of we're trying to solve for K. I feel like the initial concentration should be, it's either 0. Let me look, let me see the view an example. Because I'm just not sure about the initial concentration. View an example. Tomato, blah, 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 blah. We got that. Initial concentration is 0. Okay. So then if you do that, after 1 hour, that's fine. And then the second one, okay. Okay, that's fine. Okay. So with hours, right? So let's keep going. We are here. So K we don't know, but this is after the time has been 1 hour. So then we're gonna have a negative K, and the concentration is 13. Okay. And then for the second piece of information, the initial concentration, we're just gonna let it be. We're gonna have E to the, now again, K we don't know, but the time has been 7 hours there. So we're gonna have a negative 7K equals, and the concentration is 4 micrograms per milliliter, right? So what the thing that the view an example did, they divided the first equation by the second, right? So if we say the first one divided by the second one, we'll just work over here. We're going to get 13 over 4 equals, and when we say the first line divided by the second, the C's cancel. So then we're going to have E to the negative K over E to the negative 7K, okay? So now at this point, we have one equation, one unknown we can solve. We have one equation, one unknown we can solve, okay? So when we're dividing with the same base like that, exponentials of the same base, we subtract the exponents. So I'll just kind of work down here. We're going to have 13 over 4 equals, so if we subtract those exponents, -1 minus a -7, 7 minus 1 is a 6K. So that's going to be E to the 6K, okay? All right, so then we take the natural log on both sides. So the log here, this is going to come down. We're going to take the log here, okay? I'm going to kind of switch the order. We get 6K equals whatever this is. I'm just going to leave it 13 over 4. Divide both sides by 6. Our K is going to be the log of 13 over 4 over 6. Okay, we put that in the calculator, and that's how we're going to find our rate. Okay, so 13 over, okay. Let's see. Round to the nearest decimal. Ouch. Let's crunch that number. Okay, come on. So we're going to say the log of 13 over 4 divided by 6, okay? This should give us our K. This one. We want that to round it to 3 decimal places. 0.196. 196. Okay. Let's see. Okay, let's go back. 13. Log of 13 over 4. Okay. Let me see. You subtract those, -1, we say that's going to be 7 minus 1 is a 6, 6K, right? Mm-hmm. Mm-hmm. Take the log. Did I put my log in there? Log of 13 over 4 divided by 6.
Hey, Professor, where'd you get 6 from?
Okay, so right here, right? Let's see. The first equation, when T is 1, the corresponding Y is 13. Let me make sure I got those right. 1 hour, 13, 7 hours, we're at 4, right? So then when t is 7, we had the corresponding y was 4, right? So then what we did was we basically said this first equation, this first line divided by the second line. So that's where this came from. That canceled out our c naughts, and we had e to the negative k divided by e to the negative 7k. So then when you divide these exponents like that, you subtract. You're gonna say this guy minus this guy. So when we do this guy minus this guy, the second guy becomes double negative. So then it becomes 7 minus 6. 7 minus 1, which is 6. All right, 6k. Take the log of both sides. You get 6k equals the log of this. Divide both sides by 6. It should be this. Let's see. What else are we missing? Did we use exponential decay? Decreases exponentially, yeah. E to the kt, yeah, we got that. Let's see, what are we missing? Round to 3 decimal places as needed. 196. I'm gonna view an example. Let's see. Blah, blah, blah. To find k, yeah, we did this. Identify p of t and t. Note that p naught is unknown. After 1 hour, right, we did this. P naught, right? I think we got all of that, right? We're good to go there. 3. And I think it's something else where we're close again. We got that two thing as well. Divide the two equations to clear P naught, right? We did this. So we subtracted, right? I think we did that. Now they got a negative. Yeah, that's fine. Theirs is just different than ours. All right, continue. Solve. Natural log of that divided by -2. Continue. Okay. Oh, I think I saw something. Let me look at one other thing. I think I saw something. Continue. Continue. No, they got that too. Let me see. In one clinical study, 1 hour was 3. No. 16 micro after 1 hour, and then 3 after 3 hours, right? Let me look at hours again. So then 13. Oh, okay. I think I see it. I think I see something else. You could go there and then go there, set them equal to 1, so then it'll be equal to each other. I think I may have did my division incorrectly. That might be where it's coming. Where the error is coming in. Let me check one other thing. I think I found it. View an example. And then if we go here. We did that. So then, because what I did, the 1 was on top, right? I think what we're supposed to do is say, like you can say divided by that. So then 3 over e to the -k equals 16 over e to the -3k. So then what? Flip and multiply. Okay, I think I'm doing my division wrong. I think I just divided it without thinking about it. Let me go back and be more meticulous here. I think that's where the error is coming. It's right here, this guy. I think we did this step wrong, right? So let's kind of start there. I see something that we can do different, right? So let's do this dark blue. So we had this C naught e to the negative k equals 13, and we had C naught e to the negative 7k equals 4, right? Okay. So what I'm going to do, I'm going to solve each one for C naught, right? So then from the first one, we get what C naught equals, if you multiply, you're going to get 13 times e to the k, right? From the second equation, you get C naught equals 4 e to the 7k, right? So then if the first one equals C naught and the second one equals C naught, you can equate these two. 13 e to the k, right, equals 4 e to the 7k. So then you can get the e to the k's on one side, you'll get 13 over 4 equals e to the 7k over e to the k, and right? And it should be different than what we had before. You can see it there, right? Even if you flip those, that goes up, that's the same. And that comes down. No, that's the same thing. Let's keep going with this and see if we can get something to change. So then we get 13 over 4 equals e to the 6k, and that's what we had before. Only other thing I can think. We take the log there, divide by 6. Why would the sign change? I don't think our rounding is off. I feel like we're close, but I'm just not getting to the bottom of whatever it is, right? Because you can still take the log on both sides. You're still going to get your log of 13 over 4 divided by 6. Let's see. Screenshot. Done. Get to the bottom of what are we doing wrong. Divided by 6. A little bit early, but that's very, very rare that happens. Okay. Let me see. Let's see, they're getting a -2. Let me see. Only other thing I could think is that this might be negative. I'm not, but see, and that's why I was trying to find that negative. Like that's what I was looking for. But I don't have a good reason, because with theirs you can see it in their calculation, but it doesn't come out in our calculation. Like ours, even when we tried to change it around, we still got the same thing. Only other thing I could think is that is because it's a negative rate, like it's decreasing. Did we miss something? Did you see where I missed the negative?
I think the 6 was supposed to be a -6.
Let's see, I want to say I had that, right? So I'm going to get rid of this because I don't think this is wrong. Something got lost somewhere, right? We're going to say this, oops, undo. When we do this division, we say this minus this. -1 is a +6. Now, when I did it over here, it's the same thing that happens. Like, how are you getting a -6 right here? Because I'm not getting a -6.
I mean, I didn't get a -6, but maybe the -1 has to be a positive, and the -7 has to stay a -7.
Well, let's see. No, because the time is 1, right? We're basically plugging it into this guy here. So when t is 1, you get this. When t is 7, you get this, right? So then if we solve for c, like we did over here, you get 13. Oh, no, yeah, we got it right here. 13 e to the k. Multiply, you get 4 e to the 7k. So then we equated those two guys. If we divide by 4, divide by k, you still get a positive. Yeah, I don't. Only other thing I can think is that you have to acknowledge that it's a negative rate. Let me check one other source, and they might articulate it what we're looking for. Hang on, come on. We might have to start over. We probably took too long, but that's fine. 1, 4. Okay, I think we're okay. We got a negative. Well, before I do that, I just want to check one other thing. View an example. Okay, to model, use the exponential decay model. Yeah, we did that. P naught, and let me zoom out some. This is the initial, blah, blah, blah. That's fine. To find K, right, after 1 hour, so after 16 micrograms. Right there. What is this? 1 hour, P of T. Why is that not 16? Average 16 micrograms of the drug 1 hour after dosage. Why is it not 16? Oh, there it is. Okay. Okay, that's fine. All right. And then 3 and 3. Yep, that's fine. Okay. So we got those. I'm about to let it go. I'm just trying to see if I can find that missing negative. Spin a little bit, whatever. Now, if we said that divided by that. Now they switched theirs here. Okay, can we read it? Divide the two equations to clear P naught. See right here, they got 3 over 16. They got the e to the -3k on top. Like, why did they switch that? You can set it equal to 1. Will that fix it? If we divide by that equals 1, divide by that equals 1. So that over that equals that over that. So then no switch. That goes on top. Yeah. This is like, I feel like it might be an error because they put the -3 on top where I feel like it should be on bottom. And that's what's causing the sign change. That's what's causing it. That's what's causing it. But I can't get behind why they have theirs written the way that they do. I think they have it backwards, to be honest. But I can't, so I'm just gonna leave it as what we got for now. I think we got a -0.196. Hopefully it's the same thing, okay? So choose a correct equation. Go ahead. I'm just gonna wrap this one up. I know we kind of went in a little bit long. Okay, I think we need to go back and finish the notes, right? So I think it's just negative really because it's exponential decay. But basically our K was a -196, okay, approximately. So then if this is our K and we plug that into our exponential model, C of T C naught e to the negative KT. Okay. Okay, that might be what it is. Anyway, I'm gonna let it be. Let's keep going. Let's see. Oh, so we can plug in one of the points to solve for C naught, the initial concentration. So let's plug in the 1, 13. So if we plug in the 1, 13, we're solving for C naught, e to the negative. Now our K we just got was 0.196, and our T is 1, and the concentration is 13 micrograms per milliliter, right? So the only thing we don't know here is the initial concentration. So then that's going to be, on bottom, we're going to have this e to the 0.196 under 13, right? So we're just going to use a calculator and crunch that number. Okay, let's reload and refresh. And then we're just going to say 13 divided by E, which is here, 0.196, okay? So the original concentration is 10. We're going to say that this is approximately, we're going to say 6862, okay? So that's the initial concentration. So then our model looks like it's going to be 10.6862 e to the Okay, if I plug in the K, it's really a double negative, it makes a positive. So we're gonna say 0.196 T. If we don't get the numbers to work out, then we're just gonna introduce a negative back. But I'm just going with the numbers right now. And I'm gonna check this before I submit it, right? And so all we do, we're just gonna test those points. We're just gonna make sure, let me copy this guy. And we wanna test those points. Let me paste. Do. And I'm just going to put this in a box. Let's just test the points to make sure they work, and we'll know before we submit it if it's accurate or not. Okay.
All right.
Okay. So let me just go ahead and I'll go to my y equals and I'll put that in. We got this 10.6862. Now that rounding is obviously going to kind of make it off a little bit. 0.196x. Okay. Okay. That looks good. So then let's call on that function. So then when x is 1, we should get something really close to 13. Okay. And then when x is 7, we should get something really close to 4. Okay. So because that happens, we need to, that needs to be a negative right here. All right, so let's put our negative here. And then let's go back and change that here. Right here, we want to insert a negative and then run that model back. Okay, so again, when we plug in 1, we should be close to 13. Now that's off. Let's see when I plug in 7, what happens. 7, that's even worse. Okay. All right, 66862. Let's see if we can. Let's figure out what's going on here. Let's see. We got our K. If we plug the K in, 13 divided by, I think we did that. Here, let's just do it again. 13 divided by E 0.196. Yeah, that's what we get. Okay. Let me hop here. This one. Okay, so they're getting this 13. Choose the correct equation below. So with that, let me think. Here, let's just do the viewing example. We did all that. We got our K. Mhm. I still don't know how they're getting that negative there, but I'm letting it go for now. Okay, that's fine. We got that negative result. Okay. So to write P naught, substitute 16, we get our K. Yeah, I think we did this. Into the exponential decay, yes. Now, why is that not a double negative there? That's where I'm getting caught. So I think we're getting caught up on the negative, right? Because the K is negative, but then when they plugged it back into the exponential decay, they just did a single, they didn't do the double negative, right? That's what's kind of throwing us off. So I see what we need to do to change our see, like right here, let me get rid of this. Oh, come on. Are you dead? Okay. Right. So we got rid of the double negative, and then let's go back and redo our calculation. So then we're going to have basically this 13 divided by, that should be a negative right there. That's what's throwing everything off, is the negative, right? Okay, so then when we do that, now we're getting our 15.8. Okay, so now we're getting a better number. So let's just go ahead and account for that. Let's get rid of this. We can get rid of this. And then right here, this was supposed to be negative. Okay. And so we get 15.8148. 8148, right? So that's our K. So then we get our 15.8148 e to the negative. Okay, so now let's see if this model works. All right, let's see if this model works. Now we're going to test the model. So we get this 15.8141 e to the negative 0.196 x. Okay. So then let's test our 2 points. Okay. When x is 1, we should get 13 or something close to it. When x is 7, we should get something close to 4. Okay, that's better. That would be nuts. Okay, it was it's just flowing back and forth. You know, it's a negative that we were like losing track of, but it's fine. Okay, I didn't know. Let's back up. Come on. So then we got right here, 15.814. Okay. E to the negative. Okay, I think I got it. So it has to be either B, E, or F. It's not B. It's not F. Let's go with E. All right, that's the one that matches what we were using. Boy. Okay. The concentration of the drug. So once we get there, it says the concentration of the drug after 5 hours would be about this many micrograms per milliliter. After 5 hours, so we basically plug 5 into that. So then let T be 5. So 1 decimal place, 5.9. Okay. Okay. After how many hours will it have dropped to 4? So basically we set P to 4. We set it equal to 4 and solve.
So how do you get 5.9?
I let T be 5. I plugged 5 into the formula, the model that we just created. When you plug it in, the output is 5.9, 9.3, all that other stuff, but it says round to 1 decimal place. So then with part C, they want us to set it equal to 4 and solve.
So you just
If
plug
we-
in 5 for T.
Yeah, I plugged in 5 for part B.
Oh,
So
okay.
the model that we created, yeah. After how many hours, the concentration of the drug would be 4. So they're basically asking us to set it equal to 4 and solve. Okay. Let's go here because I have a copy of it here. Okay. So if we set this to 4, okay. So first we're going to have 4 divided by that 15. I guess we can say 15.8. Right? Just to kind of match. Then we would take the log of that. Basically, what I'm doing is setting it equal to 4 and solving. I probably should write it out. Come on. Just my device is being kind of temperamental.
Oh, so you're solving for T.
Let me write it out. Let me write it out. I'm trying to be a little bit lazy. Right here, right? I think this is the right model. This is what we got. So then basically what they're asking us to do is to set it equal to 4 and solve, okay? So first move, divide both sides by that 15. And I'm going to do 15.8 to just match what they have. Okay, divide by the 15.8, we'll get, ouch, e to the negative 0.196 t equals 4 over the 15.8. Okay, take the log on both sides. So the log of this, they cancel. On the left, we're going to have this. On the right, we have the log of 4 over 15.8. Okay. And then divide both sides by that negative. And that should give us that time. Okay. So, and let's do it here. Let's quit. Okay, clear. So we're going to say the log, we got 4 divided by 15.8 divided by, on bottom, we have this negative 0.196. Okay. So about 7 hours. 7 hours. Right here. So after about 7 hours. That was C, that was it. So I know we got lost a little bit. The thing there is because we're working with exponential decay, like we got our K, but we needed to acknowledge that the rate was decay. It was a decay rate. So even though the 0.196 was correct, it needed to be a negative 0.196. They did theirs a little bit different where it generated the negative hours. We just had to say, hey, because we're doing exponential decay, that k needs to be negative. But then what happened when we went to plug it back in and solve for C naught, we plugged the negative k into an exponential decay, so the double negative canceled. That was not the move to do. In other words, what we should have done was just do negative 0.196 and then solve that, right? So when we went back, that's why we got the initial number wrong initially, because we had an extra negative in there. Yeah, so the main thing here, we did our K, we just forced it to be negative, and then when we went back to do further calculations, we just made sure that we did not have a double negative, right? Those were the main two parts that was kind of tripping us up a bit. Aside from that, everything else is like normal. Okay. Okay, let's pull up the other one that you submitted and let's take a look at that.
All right.
I know that one was a little bit bad, but we just had to kind of, shake it off and kind of keep going. All right, let's look at this one. It says a coroner arrives at a murder scene at 7 p.m. She finds the temperature of the body to be 86.3 degrees Fahrenheit. She waits 1 hour and then takes the temperature again and finds it to be this. She knows that the room temperature is 62 degrees Fahrenheit. Assuming that the temperature of the body was 98.6 degrees when the murder occurred, when was the murder committed? I like this one. Okay. This one is fun. It's similar to the one that we just did, but I feel like it's a little bit better because we're not dealing with like exponential decay. That exponential decay was kind of being a little bit circular and kind of tripping us up a little bit. Where's my image? Let me try again. So let's get a copy of this guy. Okay. Kind of copy and delete. And let's start a new one here. Okay, and let's paste. Okay. Let's see. Now I think this one might be exponential decay again as well. It says the coroner arrives on the murder scene. She finds the temperature of the body. She waits an hour and takes the temperature again. She finds this. She knows the room temperature. Assuming the temperature of the body was this. Okay, I think this is fitted to exponential. So the temperature of the body decreases exponentially over time, right? So I think we are going to fit this to exponential decay. Time. So we're going to let capital T be the temperature and lowercase t be the time based on what, hours? Okay, all right. So capital T is going to be our temperature. We're going to find the temperature based on time. We're using exponential decay. So we're going to say T naught e to the negative KT. All right, let's see if we can keep track of this negative this time, right? Now we got some information here. They arrive at 7. The temperature of the body is, so when she first arrives, right, the temperature is 80, let me see the time. So when she first arrived, the time is what, 0? So it's been 0, wait a minute, no. Okay, we can let 7 p.m. be, it's been 0 hours, all right? Let me think about it. Yeah, I'm just gonna let 7 p.m. be, that's the time where she started everything. So 7 p.m., we're gonna let that be, it's been 0 hours. So when she started, the temperature was 86.3 degrees Fahrenheit, okay? Then she waits 1 hour, so 1 hour later, the temperature is now 83.5 degrees Fahrenheit. And again, so 0, it represents 7 p.m., okay? Now we got the temperature of the room. Okay, let's see. Because I think we do need to incorporate the room temperature. So the initial temperature. Okay, so assuming that the temperature of the body is this, when did the murder occur? So we could let the initial temperature be that. Then 98.6, okay. We're trying to solve for K. We have these two pieces of information. The room temperature, there's one thing that I feel like I'm missing. The room temperature, I'm gonna go here real quick. Okay. Okay, to solve Newton's law of cooling shown below, plus C, what is C? Is that the temperature of the room? Mm-hmm. Yeah. So the temperature of the body, so what we have is fine, we just need to incorporate the temperature of the room, so we need to say plus C. Okay. And so we're using Newton's law of cooling. Okay, so let's just say, let's incorporate the C based on that. So the part that we're missing, we're gonna say plus C, which is the room temperature, okay? So now let's plug in this information that we have and see what happens, okay? Let me think. That's gone, that should be that. That should be the initial temperature of the body. So what are we missing there? Let me see, if we plug that in, we're gonna have that T naught. That should be 98.6. Let me check one other thing. View an example. Mm-hmm. Mm-hmm. 98.6, that's fine. Okay. Mm-hmm. Okay, so we need to solve for that constant. Let's see. So right here, the T naught, let's just solve for that. Or so if we plug in what we have, right? We're gonna have what? T naught e to the power 0. I think C is the temperature of the room, which is 62. So we're gonna say plus 62 should equal 86.3. Okay. So from here we can solve for T naught. Long story short, T naught is gonna be 86 minus the 62. Clear? Oh, come on, stop. So let's do the 86.3 minus 62. Okay. So then 24.3. So that's just a constant. 24.3. Okay. So let's see. We did that. We got T naught. So it looks like our temperature of the body based on time is going to be this, just this constant e to the, we have our K. Okay, I think we're still trying to solve for K. So then let's use the second piece of data, right? We use the first piece of data to find T naught. We need to find that K, right? So let's plug in the second piece of data. So then let's go ahead and plug in the T naught, which is this 24.3, okay? E, we're still trying to solve for K. The time has been 1 hour, so it's gonna be 1K or just K. The C, the room temperature is 62, and the output should be 83.5, right? We have one equation, one unknown we can solve. Okay. I guess I'll go ahead and write out the exact thing. If we subtract 62 to the negative k, all right? 83.5 minus 62. 21.5. Now, I remember doing this in a little bit different way. 21.5, but this is fine. Let's just keep going. Divide, so then we get this. Okay. Take the natural log on both sides, we'll get this. Okay. And then both sides by negative, so the k that we get is this. Okay. And with that, we get that the temperature of the body based on time is going to be our T naught 24.3 e to the, let's calculate that number for the k. So for k, we're getting negative log 21.5 over 24.3. Okay. And so for our k, we get this number. So 0.12, I'm gonna put 24 for now. T, right? Plus the room temperature. Oh, my pen just died. This real quick. Okay. Plus the room temperature. The room temperature being 62, I think, right? 62, right? So this is the model that we get. Okay. And then so we need to confirm that those original temperatures fit this model. So initially, I think I was using just exponential decay, but we needed to use Newton's law of cooling, right? So the only thing that we had to change, we needed to add the room temperature to our model. Okay. Let me get a copy of this. Like this.
So we need to check to see if this.
Yeah, that's exactly what I'm doing now. Right here, I want to make sure that these guys work.
Okay. If this represents like the model that we got.
Yeah, based on Newton's law of cooling. And so we had to kind of adjust what we had initially. So I'm gonna see if our data matches. If we at least can match our data to this model. So then I'm going to do this 24.3 times e to the power of 0.122. I took my decimal a little bit longer than I probably needed to, but that's fine. And then we're going to say plus 62. Okay. So then I'm going to call on my function. And when x is, let's see. Now, when x is 0, we should get 86.3. Okay. And then when x is 1, we should get 83.5. Because 1 hour later. All right. Let's go back and look at our work and see where we may have made a mistake. Okay. T naught e to the negative kt, right? But this is times 0. So then that's T naught plus 62, 86.3, right? We get this for T naught, right? Let me just check one more time. 86.3 minus 62, okay. 24.3 looks good. So then we use the second piece of information. So T naught, which is 24.3, e to the negative kt. T in that case is 1 because it's been 1 hour later. Okay, so we got our negative k plus the room temperature, and the output should be 83.5. So then if we say 83.5 minus 62, we get this. Okay. we got our 21.5. Divide by that. It should be the log of that. So then a negative of that. All right. Okay. So then if we say a negative log of 21.5 divided by 24.3, okay, 12. Now, only other thing I could think is maybe it's our rounding. We could leave it exact and do our calculations. Let's leave it exact, all right? Let's try leaving it exact, unless we might need to reintroduce that negative, right? I think we're missing our negative because it's exponential. Okay, I think that's what we're missing. Right here. Right here. And see, and it's like, that's what it is. Like, you get a result, you say, okay, if this is correct, then this should be the case. We got an error, so we're missing something. We went back over it again, just took our time. We were missing a negative here, right? So let's incorporate that negative and see if that fixes it. It should fix it. Let's insert this negative and redo the thing right here. So let me call. We should get our 86.3, and then after 1 hour, we should get 83.5. Okay, so yeah, man, just missing that one negative. Like, threw everything off, made us have to go back and like figure out where did we miss, right? So we forgot our negative at the end. Okay, so we found it before we submitted it, but that's what happens. That's how these things go. So now this fits our model. I feel like the hardest part is over. Again, we had our negative right here. That's good. Okay, so I think we're ready to go to answer the question, right? The hardest part is over, right? So this is the temperature. This is the temperature of the body based on time. So then it says that the temperature of the human body is 98.6 degrees Fahrenheit. So based on this model, we want to see how long ago was the temperature 98.6, right? So all we're going to do is set our model equal to 98.6 and solve for t. I feel like Glass Onion, like the detective. I just really enjoy this because it breathes life into the experience of mathematics, right? Which is a Netflix movie. It's like it's just a fun movie, the whole Glass Onion, Knives Out series or whatever. Anywho, let's set this equal to 98.6 and solve. So then we get this 24.3 e to the negative 0. And I'm gonna leave it as 1224 because I think that worked for us. T plus 62. When was the last time the temperature was 98.6 degrees Fahrenheit, right? So if we solve for T, subtract this, I'm going to reverse the order, subtract 62. So we're going to have 98.6 minus 62 equals this. Okay, let's clean it up. Okay, we're still solving for T. We're going to divide both sides by the 24.3. So whatever this answer is, divided by 24.3. What's left on the other side, e to the negative 0.1224 t, okay? Take the log on both sides. Okay. And on the other side, we're left with this. Okay. And divide both sides by that negative, and t is ultimately going to be, we got this 98.6 minus 62 over 24.3. We're taking the log of all of that, and we're saying this divided by this negative 0.1224. Okay, that's the exact result. So then let's get our approximation. So we're going to say the log Now the numerator, we got this 98.6 minus 62 divided by 24.3, okay? So that closes off the log. Then we want to say whatever that answer is, we want to say divided by is negative 0.1224, okay? So then, so go back by about 3 hours, maybe 3.3 hours. So she started at 7, so in the 6 o'clock hour, right? A little more than 3 hours ago. Because 7 minus 3 is 4. That's a little bit before, just before 4 p.m. So in the 3 o'clock hour. Late 3 o'clock hours. So then they would go to the security camera, or okay, say who was here around a little after around 3:30 or just after 3:30. That's where they would start looking in the 3 o'clock hour. That's where they would start. Then round to the nearest hour. I guess the nearest hour is 4, right? Because the nearest whole number is 3. So 3 hours earlier would be 4 p.m. So approximately 4 p.m. Okay, it's actually a little bit before 4, but they say the nearest hour. Now, if we need to go back through now, one thing that we did make, one error we made initially, we were using the wrong formula. Then I saw this, I was like, oh, we needed to incorporate the room temperature, right? So Newton's law of cooling. It's still exponential decay, but it's just the extra C, which is the temperature of the room. Okay. Yeah, those were intense. Those are good questions. Those are good questions.
Professor, where'd you get the 4?
4.
Because in the calculator, I'm pretty sure it was like a negative 3 point something.
Right. So when we calculated that final number, we got negative 3.3 something. Yeah. So it says to the nearest hour. So the nearest hour is going to be negative 3. So then 7 minus 3 is that's where the 4 came from. It's really like late 3 o'clock hour, but they just want an approximation. So the nearest hour is 4 p.m. instead of 3 p.m. Does that make sense?
Yes.
Yeah, those were good questions.
Because they
Like
said approximately to the nearest hour.
Yeah, because remember she started this whole thing at 7 p.m. So this T says the murder happened it was about 3 hours ago when that was the last time that the body temperature was 98.6. Right? Because the nearest hour is 3 hours. So then 7 o'clock minus 3 hours puts us at 4 p.m. All right, I'm gonna give you a bath. I see you itchy scratchy. I have to give you a bath and put everything in the wash. Get out, that hurts. Ooh, those are good questions. They made me think. But yeah, you have to like just take your time and like just keep kind of going back and forth until you get to the bottom of every little part. But this is another reason why I use Pearson. Like if you ever get stuck, I know the viewing example can be kind of like detailed, but you at least have an explanation for each question. And so with somebody like me or a tutor or a classmate, somebody that gets it, then along with the viewing example, you can get to the bottom of all the parts. All right. So that's part of the reason why I use Pearson. Because sometimes I'm like, wait a minute. And then usually like 90% of the time, the questions have an explanation right next to the problem or whatever. Okay, we can work on some more or call it a day, whichever you feel up to.
Yeah, that's it.
Okay. All right. So I guess like what I'm thinking is you know, if something like that comes up on an exam, it's still going to be fair game, but you know, we can talk about it. Like, just do the best you can. You know, we can work on it together, and then I could possibly like give you credit for it retroactively. You know what I mean? Like after the fact. So just do the best you can. Like, I'm not trying to be super strict. I'm not trying to have you do too much. Like, I'm just trying to expose you to these concepts, and then you know, just you know, it's really just exposure. Okay. All right. Let me go ahead and make a copy of this available. That's what I'm trying to do. This is spring calculus notes, handwritten notes. Yeah, this is week 6. I guess on Wednesdays we kind of do homework sets, but that's fine. Just go like this. Okay, did you have any other lingering questions before we go?
No, sir.
Okay.
That's it.
So if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day, okay? Take care. Peace.
All right, bye.